Hi everybody, this is Dr. Bricker here with a video for Chapter 28, Part 1. Before we get into Chapter 28, though, there's a little bit of unfinished business from Chapter 25. So we'll talk about that and then we'll get into Chapter 28 and you'll see why. So this section of Chapter 25 deals with the photon model of electromagnetic waves, and then that's what Chapter 28 is about. So 25 going into 28 is kind of a transitional chapter. So photon model of electromagnetic waves. So if you remember Chapter 25, we were talking about electromagnetic waves, and we learned that light is a wave, and we just saw wave properties in Chapter 17. But sometimes light behaves like a particle. As it says here, electromagnetic waves have particle-like nature. It just depends on what they're interacting with. So we'll label these sort of like massless particles as photons. So photons are the particle-like component of the electromagnetic wave. And really, you just see wave behavior if you're trying to squeeze light through a small opening. In some cases, you see this sort of like particle-like nature of electromagnetic waves. Okay, and here's one experiment that sort of shows this. So if you see here on the right-hand side, this is increasing intensity as we go down. So if light were behaving as a particle, this looks like you're just throwing a bunch of stuff against the screen, and here you're throwing more, and here you're throwing more. So that's an example of light behaving as a particle. You would just think that this would be dimmer, the one up here, if the intensity was not as much. But really, when the intensity is not as much, you get the splotchy picture where there's things that sort of are missing. So it's not just dimmer, it's that there's actual parts where the photons are not actually hitting. And then down here, the increasing intensity, you have a full picture. Okay, and then the one in the middle, sort of in the middle, intermediate idea, where you still have some missing spots where photons didn't hit, but here, when you see the picture of all the photons hitting, when the intensity is greater, you get a full picture. Okay, so again, if it was just behaving like a wave, this would just be dimmer. You wouldn't have the splotchy appearance there. So that's sort of evidence that light sometimes behaves as a particle. And we'll see more evidence in just a few minutes. So as it says here, in actuality, a dim photo shows that only a few points of the detector registering the presence of light. Instead of the whole thing just being dimmer, you see that there's parts missing. So kind of a synopsis of what I've just said. Okay, so the photon model for electromagnetic waves consists of three basic ideas. These waves consist of discrete massless particles called photons. So on a nice sunny day, if you go outside and you're in the sun, you feel warmer. I like to think of it as photons actually hitting me. That's why I feel warmer. If you go in the shade, not as many photons are hitting you. You're still outside, but you just feel warmer in the sun because you're getting hit with these photons. Okay, good. And photons do, just like electromagnetic waves, travel at the speed of light. So 3 times 10 to the 8th meters per second. Okay, the energy the photon has is equal to h times f, as you see here. So h is Planck's constant. Maybe you've seen this from chemistry or thermodynamics. So h is 6.63 to the minus 34th joules times seconds. And then f here is the frequency. So the energy is just, if you know the frequency, you know the energy. It's just related by a constant. So don't forget also that we have the speed of light. The speed of light is the frequency times the wavelength. So you can solve for the frequency in this formula. C over the wavelength is the frequency. And then we can plug it in here and have another way of writing the energy of a photon. So energy, still h, but then F is C over the wavelength. So you could write it like this. Energy is hc divided by the wavelength. And here's a little shortcut. H is a constant, C is a constant. So if you plug in the value of H, the value of C, you get this. 1240 eV times nanometers. And we'll use this when we do the photoelectric effect, and we'll talk about what this unit of electron volts is. But H times C in electron volt nanometer units, it's 1240 electron volt nanometers. This little shortcut will save us some time, and you'll see how that works out in just a minute. Okay, and the third postulate here, the superposition of a sufficiently large number of photons, has the characteristics of a continuous electromagnetic wave. So when you add them all back together, you still have a wave. Just depending on what the wave is interacting with, sometimes it's beneficial to look at this photon model for light. So far we've had geometric optics looking at light like a ray. That was chapter 18. Chapter 17 we looked at light behaving like a wave, and in this chapter we look at light behaving as a particle. In chapter 28. We're not quite there yet though. Depending on the energy, a single photon can cause molecular transformation. So these photons have an energy, starting with like radio waves, which don't have a lot of energy, all the way up to gamma rays, which can cause damage to your DNA, actually. If you're out in the sun, you get some ultraviolet hitting you, maybe don't get damage, or maybe you do get damage. You get your skin, maybe you get a sunburn. Okay, so that's what's happening. These photons have enough energy they can do some damage. Okay, so here's a few different energies associated with different processes. So breaking a hydrogen bond between two water molecules, 0.2 24 eV. Energy released from ATP, 0.32. Breaking the bond between atoms in a water molecule, 4.7 eV. And maybe you've seen this number from chemistry. Ionizing a hydrogen atom, and that's another way of saying removing an electron from a hydrogen atom, 3.6 eV. And then the unit conversion between electron volts and joules. So electron volts, just another unit of energy. So 1 electron volt is 1.6 to the minus 19th joules. So joules, still the SI unit, but people that do a lot of work in this area like to use electron volts. So it's good to know the electron volts. So 1 eV, it's 1.6 to the minus 19th joules. Okay, it's the energy to take 1 electron through a potential difference of 1 volt, and you get 1.6 to the minus 19th. Okay, all right, very good. So the electromagnetic spectrum, then, this is also from chapter 25, looks something like this. Down here we've got AM radio. Here's the associated energy in EV. Here's the wavelength. And then as the wavelength gets smaller, the frequency gets bigger, and you can see the energy changes. So all the way up here at gamma rays, 1 times 10 to the 4th eV. So gamma rays can be produced, say, in a supernova, something like that. X-rays, maybe you've had an X-ray before. You can see that's part of the spectrum. Ultraviolet here. So visible light, the part that we can actually see, red, orange, yellow, green, blue, indigo, violet, that's just a really small part of the whole electromagnetic spectrum. We're concerned with it because that's the colors we see in. That's what we can detect with our eyes. Okay, and then you've got infrared, microwaves, FM radio, TV, and AM radio. Okay, so all of these, though, travel at the speed of light, 3 times 10 to the 8th meters per second. They just have different energies because they have different frequencies. Okay, same thing that we had before. H times F. You can, if you know the frequency, you can calculate the energy, or HC divided by the wavelength. Okay, good. So you can see also particle-like behavior occurs here when the energies get greater. Wave-like behavior down here. Okay, very good. So electromagnetic waves span a wide range of wavelengths, as you just saw. Radio waves, wavelengths of many meters, but very low energy photons. Gamma rays, X-rays have very short wavelengths, so the smaller the wavelength, the bigger the energy, and higher energies. Visible light, ultraviolet, infrared here can be described as waves or photons, really just depending on the situation, what they're interacting with. Okay, very good. Electromagnetic wave is independent of currents or charges. So you don't need anything for these waves to travel through. You do need something to get them started in the beginning, and then you can have a wave. So changing electric field produces a magnetic field. Then you have a changing magnetic field produces an electric field, going back to chapter 25. That's really what an electromagnetic wave is. Okay, radio waves and microwaves are generally produced, as it says here, by the motion of charges through an antenna. And we talked about that when we looked at chapter 25, what actually was an electromagnetic wave. Well, you produce an electric field maybe from nothing to something. That means you have a changing electric field. You produce a magnetic field, which then went from nothing to something. We know from Faraday's law, changing magnetic field produces an electric field, and so on and so on and so on. And that's how we discussed producing electromagnetic waves with like an antenna. Okay? Something like this. So notice here, this is a dipole plus minus. Now what if it flips around? Minus plus. So the electric field has changed. Now if you're over here and you're an observer, here's your eye. Whoops. There's your eye, and you're looking at this thing. You see an electric field, but now the charges have flipped. Now the electric field has flipped. It doesn't instantly flip at your location. It takes some time for that information to get to you. That information getting to you is what the wave actually is. Okay, so pretend you have this dipole in your room. You're across the room. Somebody flips it around. You don't instantly know it's flipped around. That information travels to you at the speed of light. Okay, and that's the wave part. Okay, so here's some kind of signal generator over here. This side's all negative, this side's all positive. Then it's going to, you're going to have an associated electric field. And if this thing keeps flipping around, the electric field's going to keep flipping around. Having a changing electric field produces a magnetic field. Okay, and then also from chapter 25, this is the direction that the wave travels. So if you take your finger at E, so let me just reference this part. The electric field, this is your opposite of me, but the electric field's up, the magnetic field's towards me, the wave is traveling that way, and it travels at the speed of light. Okay, good. So radio waves can also be detected by an antenna. So if you have an antenna set up and this wave travels to you, the electric field can interact with the antenna, and you could read the signal that way. So the electric field of a vertically polarized, again, it goes back to chapter 25 as well, interacts with the electrons in the antenna, moves them around, and that's the signal that you detect. In my attic here, I've got an antenna, and I pick up the electromagnetic wave from Chicago, and my antenna in my attic sends a signal down to my TV. I have all these free channels, and it's nice now. There's like 4 channel 2s, 4 channel 5s or something like that. I think 3 channel 7s, 5 PBS, all for free. I mean, we pay taxes. That's where it's coming from. I also can pick up the South Bend stations. I'm currently in Valparaiso. Okay, so my antenna up there is just reading the radio waves, and the TV's decoding it. I'm getting this free digital signal. Okay, this is just a rule of thumb. People that work with this, the antenna should be about 1/4 the wavelength to be able to get a nice signal. My antenna in the attic only costs, I think, $50. It's maybe about this big. It's up in the attic. It comes with a little control box, so I press a button and the antenna rotates around until the signal comes in clearly. So it's a nice setup. Okay, so AM radio has lower frequencies, longer wavelength. That's the way it works from the formula, remember. HC over the wavelength. The bigger the wavelength, the smaller the energy. Okay, so it says here, instead an AM radio detector uses a coil of wire wrapped around magnetic material to detect it. So remember, the electric field part's going up and down. If you you have an antenna here, the electric field's going up and down. You can get the signal that way. The way you can get electricity from magnetic fields is you have to have a changing magnetic field going through a loop. So if there's a loop, magnetic field's going through and changing, you can get a signal that way. So if you're old like me, our old TVs used to have a straight antenna on the back and then a round one. The round one was to pick up the signal going in and out. The straight up and down one was to get the electric field part. So magnetic field part like this, electric field part up and down. Okay, excellent. So vertically polarized AM radio wave is traveling to the right in this picture. How should you orient a coil antenna to detect the magnetic field part? Okay, so good. You've got to get the magnetic field part going through the loop, and that's what's being shown here. So you want it to be able to go through like this. You wouldn't put the antenna like this because none of the magnetic field part would go through it. You want there to be a flux through the area, just like Faraday's law. Okay, so that's kind of a synopsis of what I've said there. You want to be able to catch the magnetic field. If you turn the loop like this, you're not catching any of it. You're getting no flux, maximum flux. Okay, good. That's kind of a synopsis of what I've said. Okay, you can try it yourself. Airplane passengers are asked to turn off portable electronic devices during takeoff and landing. To see why, hold an AM radio near your computer and adjust the tuning. As the computer performs basic operations, opening files, etc., you'll pick up intense static because the rapidly switching of voltages, so changing electric fields due to the changing voltages, produce magnetic fields, etc., and you can actually pick this signal up if you have a radio sitting here. Okay, so it's reading what the computer's doing. Okay, very good. When my wife brushes her teeth with her electric toothbrush and I'm watching TV, the whole picture is scrambled. So that electric toothbrush is giving off electromagnetic waves, and those are actually being picked up by the TV. Okay, good. Radio waves and microwaves in materials with no free charges, the electric fields of radio waves and microwaves can still interact with matter by exerting a torque on molecules. So with the microwave, you've got a water molecule, which is a polar molecule, which means, the positive part and the negative part are slightly askew from each other. So pretend this is a water molecule, and you have an electric field like this, it will line up. You flip the electric field this way, now it's going to line up because it has a torque. Flip the electric field this way, it's going to line up. Do this quickly, the whole thing happens like that. The water molecule keeps moving around and around and around. Due to friction, it heats up the water. So when you use a microwave, really what you're doing is just having the water molecules flip all around, and due to friction between the water molecules and other molecules, you heat your food up that way. Now you do not want to put like a metal utensil in your microwave, because changing electric field, acting on electrons, you'll have sparks going everywhere, so don't do that. But if you want to just move water molecules around, use a microwave, move the water molecules around. Due to friction, they heat up other molecules in your food, and that's how that actually works. Maybe you've actually done that today. So have a large dipole moment, which, going back to the beginning of the semester, just means positive and negative charges are separated from each other. Rotate in response to the electric field moving around, and due to friction, your food is warmed up. Okay, infrared, visible light, and ultraviolet. Oscillating charges in an antenna produce radio waves that are replaced by individual atoms when producing higher frequencies of infrared. So visible light and also ultraviolet. So if you forget how to remember this, Roy G. Biv, this is the visible spectrum. So that's this is violet, red, orange, yellow, green, blue, indigo, violet. So ultraviolet is bigger than violet. And then infrared is over here. Infrared is over here. So it goes infrared, visible. This part's the visible part. And then we have ultraviolet. So that's the order. And the increasing energy goes this way. Okay, so this is made from, as it says here, atomic radiation. Okay. So humans, we don't emit light in the visible spectrum. So we're not emitting this. You don't see me with your eyes because I'm emitting this, but I'm reflecting visible light. You can see the light that I'm emitting. I'm emitting infrared, so you need special goggles, and you could actually see what I look like in terms of the light that I'm actually emitting. Okay, good. A little bit of chapter 18 thrown in there. Okay, so now we're finally ready to get on to quantum physics, things like the photoelectric effect, uncertainty principle, stuff like that. Okay, so this is a false image made by a tunneling electron microscope. So the very end of the chapter gives you a little bit more details, but this is on the nanometer scale, this picture, that you see here. Okay, so more about that at the end of the chapter. Okay, so this looks like an interference pattern that we saw when we did chapter 17. You know, maybe it's a diffraction grating. I don't know how many slits it is, but you might get a picture like this. But you can see there's parts that are missing. So if light was behaving like a photon, you might get a splotchy picture like this. It's just not dim. There's actual points where the photons have not hit. So you get this sort of image if you have a low intensity of light. Okay, so this would happen if you have just discrete chunks, or in other words, photons coming in. So where some are missing, the photons must not have hit yet. Okay, so sometimes light behaves like a wave, sometimes it behaves like a particle. This chapter is all about looking at light behaving like a particle. Okay, and this is a picture made of electrons actually going through a diffraction grating. So sometimes matter, like electrons that have mass, you actually can see their wave-like behaviors. Okay, so electrons are really small. You can squeeze them through small openings. Their wavelengths are on the order of the opening, and electrons would actually hit the screen something like this. Okay, so things that have mass and are moving have a wavelength associated with them. So electrons do, but we also do. You'll see that in this chapter too. You can calculate what your wavelength is. Once you do that, you'll see your wavelength will never encounter an opening that small. You'll physically never be able to go through an opening that small. Okay, so X-ray and X-ray diffraction, just to save time, we're going to skip section 1 of this chapter and go right into the photoelectric effect. Okay, so this is what Einstein actually won the Nobel Prize for, the photoelectric effect. So the first hints about the photon nature of light, looking at light as a particle, came with the discovery that negatively charged electroscopes could be discharged by shining UV light on it. So here's an electroscope. It's been charged up. You put a negative charge on it. These are gold leafs down here, these two things. So when they become negatively charged, they can actually move and they separate. This would be kind of like if you got a bunch of negative charge on your hair and your hair stood out. You know, electrons don't like to be by other electrons, so they repel each other. That's why the leaves of the electroscope are repelled. So when you shine UV light on this, so UV light is hitting here, it's just photons that have a certain energy. Electrons are able to grab a hold of this energy from the photons, and they are liberated. So these ejected photons are ejected because they get enough energy to be ejected. And then the leaves go back like this, so you're able to actually discharge this. So this is the photoelectric effect. Electrons can grab a hold of some energy, have enough energy to escape, and they do in this picture here. So here's what an actual device might look like to experimental device to actually look at this photoelectric effect, more so than just the electroscope. So here's a cathode, and here's an anode. And it's called a cathode because it's negatively charged. You can see this side is hooked up to the negative side of a battery. This side here is hooked up to the positive side of a battery. Okay, so you can shine light on here. The light hits the cathode where there's electrons. The electrons are freed. This was negatively charged. This was positively charged. So when you free the electrons from the surface, there's an electric field here. Electrons don't want to be over here on the negative side. They head over to the positive side. And you actually can have a current flow. So if you have an ammeter here, you'd actually measure you'd measure a current flowing through here. Even though this is not directly connected, you've got free electrons there. So notice this has current going that way. That's conventional current. So pretend positive charges are moving to the right. In reality, you have negative charges moving the other direction. Okay? And you could actually measure this current. So this is a device to be able to measure the photoelectric effect. Okay? So when UV light shines on the cathode, a steady counterclockwise current passes through the ammeter. Okay, and that's so-called conventional current. Okay, so it says UV light here. It has to be light that has enough energy. You can't do this with like radio waves. Radio waves don't have enough energy to to free the electrons. And the electrons can't store up the energy from a whole bunch of radio photons, if you want to call them that, coming in. The photon that comes in has to have enough energy on its own. The electron will grab a hold of that energy, and if it's enough, it'll be freed. If not, it's not. And then if there's any left over, that energy can turn into kinetic energy. And we'll talk about that in just a minute. So this incident light causes electrons to be ejected at a nice steady rate. There is no current if the electrodes are in the dark, so electrons don't spontaneously leap off. So you could turn the light off and nothing's happening. You turn the light on, the light hits the cathode, you free some electrons. There's a voltage set up here, and you actually see a current flow. Okay, but the photons have to have enough energy. The battery establishes this adjustable potential to actually get some charge to flow. Guides it across. Okay, very nice. So the current is, here's a few things about the photoelectric effect. The current's directly proportional to the light intensity. So if the intensity doubles, the current doubles. So intensity means you shine more of it on there. The current appears without delay when the light is first applied, but there is a threshold frequency. So you have to have enough energy. The photon has to have enough energy to liberate an electron. If it doesn't, nothing happens. And you can't store up the energy from several different photons. It's the energy of one of the photons. Different metals have different threshold frequencies. So sodium metal has a different something called work function than aluminum would, for example. You can actually tell what the metal is by how much charge you are liberating. Okay, so if the potential difference that you set up is more than about 1 volt positive with respect to negative, the current changes very little as the voltage is increased. If the delta V is made negative, the voltage across there is made negative, the current decreases until you have something called the stopping potential. So why would you want to stop this from happening? We can figure out the work function if we know the stopping potential. So this is more of a experimental idea. Why would you ever want to do that? You'll see why in just a minute. Why you'd want to stop it from going. Okay. Essentially, that we're taking all of the kinetic energy and turning it into potential energy when you stop it. But more about that in just a minute. The stopping potential is the same whether you have intense light or weak light. Okay, so this is the potential that stops all current from flowing across. Remember, it looks like this. Now, if you flip the battery around and electrons try to come across, if you set up this flipped around with enough voltage, you can stop all of them from coming across. They're liberated, but you're stopping them, basically. Okay, so here's a picture here of current versus frequency. So you get no current at all until you hit the threshold frequency. Okay, and then once you hit the threshold frequency, that's when you get current to actually flow. Okay, so here's where there's no current flowing. This is the stopping potential. You flip the battery the other direction and you completely stop all current from flowing. And again, why would you want to do that? We'll see that in just a minute. And this picture is just for a given frequency. Okay, so you've picked a frequency. This is what you have. So for weak light, you get a certain amount of current. For intense light, you get more current. But you could stop them all if you have enough stopping potential. Okay, very good. So you have to have a minimum energy to free an electron, and then once you free them, if you've just freed them, if you set up a voltage, they can drift across and you can measure a current. Now, if you have more energy than you need, the additional energy goes into the kinetic energy of the electron, and we'll see that in just a minute. But there is a minimum energy that you need called the threshold energy, called the work function here. So this is equal to H times the cutoff frequency, or if you want to do it like this, HC over the biggest wavelength that you could possibly have. Okay, so the photons have to have at least this much energy, or in other words, this high of a frequency to be liberated. And different metals have different work functions. Sometimes it's easier, sometimes it's harder. Here's a table of work functions, actually. So potassium, it's a lot easier to liberate an electron from potassium than it is from gold. So gold really holds on to electrons tightly. Potassium doesn't, and then you have a whole range here. So you can tell what element you actually have if you set up this photoelectric experiment, measure this work function, you could figure out what you're dealing with. Okay, so an electron with energy of this inside a metal loses energy as it escapes, so it emerges as an electron with kinetic energy equal to this value. It's probably better to look at this formula, actually. This one makes more sense. So this is the kinetic energy that the electron could possibly have. Now, when it says here energy that the electron has, where did it get the energy from? Well, it got the energy from the photon that came in. So this is the energy that the photon had, H times C, or sorry, H times F. And then you got to subtract off the price to be liberated. So this is the energy that you get from the photon that comes in. Subtract off the minimum amount of energy. That's the energy to be liberated, the work function of the metal. That's another way of saying that. And whatever's left over goes into kinetic energy. So let's just say that one more time. This is the energy that the photon had. Subtract off the price of admission, or the ticket, however you want to think about it. That's the work function. Subtract out the work function. Whatever's left over becomes the kinetic energy that the electron will actually have. Okay. I wrote HF. Remember, this is also HC divided by the wavelength. Okay. Hopefully you can, let me fix it. HC divided by the wavelength. There we go. Maybe not any better. There we go. Okay. So in the experimental device that you saw, the electrons, after leaving the cathode, move out in all directions. The purpose of setting up a potential difference is to guide them across the tube where they're liberated. So some will reach the anode on their own, but if you set up a nice potential difference, you can direct them all across. Okay. So in the photoelectric effect device also, if the anode is positive, it attracts all the electrons to the anode. Further increasing this voltage doesn't cause any more electrons to reach the anode. And then that's the point where you don't get any further current because of there being a potential difference there. Okay, so set up a nice positive, negative. These are freed electrons. They're going to come across there. Okay, very good. So in the photoelectric effect measuring device, the whole thing that we've been talking about, if the anode is negative, so if the other side is negative, if this is negative and this is positive, you'll tend to stop them from coming across. And again, you'll see, why would you want to stop them? We'll see why in just a minute. So if they've got enough energy to begin with, even though this is negative and this is positive, they might make it across. But if you keep making this more and more negative, this side more and more positive, this side more and more negative, this side more and more positive, then you'll eventually stop them all from coming across. That's the stopping potential when that happens. Okay, so in that case, the change in electrical potential energy, so we saw this earlier in this semester, times delta V. We saw that earlier. That's really what this formula is. So we're putting in the E, it's an electron, so the fundamental charge. That's what Q is in this case. So you're taking all of the electrical potential energy, and it's equal to minus the change in kinetic energy. So that happens when you have the stopping potential. So remember what's actually going on. The electrons are freed. They have some kinetic energy. Now you've set up the battery backwards in a sense, and you're taking all of that kinetic energy and turning it into electrical potential energy. So that's what we see here. Maybe another step would have been writing E times V stop. That's the electrical potential energy. where did it come from? Well, the kinetic energy, that's where it came from. So this kinetic energy turned into electrical potential energy. Okay, good. So if you were able to measure the v-stop where you have no current anymore, you know what the maximum kinetic energy of the electrons must have been. So why do electrons leave the metal at all? So this is Einstein's explanation. So the first explanation was maybe heating it caused this electrons to be emitting. The problem with this idea was that electrons began to leave as soon as the light hit the metal surface. The surface didn't have to heat up. As soon as light hit, bam, electrons are freed. So it didn't have to be warming. Didn't have to warm up. This heating idea also doesn't explain the threshold frequency at all. Okay, so there were problems with just heating it up. So Einstein explained the photoelectric effect by extending some work by, maybe you've heard of this guy, he's got a constant named after him, of Planck, who thought of this whole idea in terms of discrete amounts of energy. So when you, say you go into a building and there's a ramp, like in Westville there's a ramp going into the tech building. You walk up the ramp, you could be anywhere on the ramp that you want to. Or maybe you take the stairs. Now in the stairs, there's just a stair here, a stair here, a stair here. You're not standing anywhere between those steps. So quantum mechanics is this idea that energy is quantized. You can only have certain steps that you stand on. In our world, we could stay wherever we want to on the ramp. In the quantum world, you have to be on the first step, the second step, the third step. You could even be on the ground level. And Planck's idea was that you only have a certain amount of energies, and 0, HF, 2 times HF, 3 times HF, nothing in between. So Einstein ran with Planck's idea that, well, maybe these photons of light only can have individual values. And we see then that the work function is just one number, for different metals. It's related to H times F. Okay, so here's Planck's constant in SI units. You saw that earlier. Here's Planck's constant in EV times seconds. Okay, good. So again, Einstein ran with Planck's idea. Electromagnetic radiation is quantized. It can only have certain values, in other words. So light is not really a continuous wave, but instead arrives in these little packets called light quanta. We've been calling them photons. And then we see the energy of each photon. Okay, so it's almost in a way, because we live in a world where things behave like particles mostly. I mean, we see the wave effect sometimes, but mostly things behave like particles. So I think you have more intuition if you think about light as actually being a particle. It has a certain amount of energy. It can interact with different surfaces, and in some ways it's a little more straightforward actually than thinking about it as being a wave. Okay, so let's see. Here's an example. Ultraviolet light at 290 nanometers does 250 times as much cellular damage as an equal intensity of ultraviolet light at 310. Okay, so you got 290 and then you got 310. So 290 nanometers has more energy. So the smaller the wavelength, the bigger the energy. There is a clear threshold around 300 nanometers. Okay. What is the energy in EV of photons with a wavelength of 300 nanometers? Okay, so let's use our little shortcut here. Energy HC divided by the wavelength. Now I'm going to use H times C of 1240 EV nanometers. You could plug in H, plug in C, plug in the wavelength. You could do it that way, and that you get a perfectly good answer. I'm going to use the little shortcut. H times C gives you 1240 EV nanometers. This is useful when the wavelength is in nanometers and they want the answer in electron volts. And then the wavelength we're talking about is 300 here. 300 nanometers. Okay, so the nanometers parts cancel out, and then you're just left with EV. Okay, so 300 goes into 1240. Looks like 4 times or so. 4 and 4/30ths or something like that. So, a little bit more than 4 eV. Okay, good. So I'll just put 4 point and you can work out the point. Okay, very good. So that's a little trick for you. Okay, so it looks like we're solving it here in another way. Oh, 4.14. So if you want, you can get the frequency. This is a longer way of doing it. The speed of light divided by the wavelength, this will give you the frequency. And then once you have the frequency, you can use the formula h times f. So here's h in eV times seconds times the frequency. Remember, a hertz is equal to a 1 over seconds. So when you think about hertz as 1 over seconds, the seconds cancel out this second. Okay, let's think of it as 1 over seconds. That second cancels out, so you're left with eV. Good, so about 4.14 eV. This way or that way, however you want to do it. Okay, so this number is reasonable. We saw in chapter 25, really earlier in this video, splitting a bond in a water molecule requires about 4.7. So the number we have is realistic. Okay. So Einstein framed as 3 postulates about light quanta, in other words, photons like this. Light of frequency f consists of discrete photons, each having an energy of h times f. Don't forget, you could also write it as hc divided by the wavelength. Light quanta are emitted and absorbed all or nothing. So like with the photoelectric effect, you either get all the energy or you get none of the energy. You can't just take a little bit, and you can't store up energy from multiple photons. It's one or nothing. Oh, as it says here, one electron is going to absorb all of that energy, or it's not. Now, if the energy is not high enough for the photoelectric effect, then you're not going to absorb it. If the energy is high enough, then you will, and if there's any left over, it will turn into kinetic energy. Okay, good. So let's see here. Say the photoelectric effect, light shining on metal is a torrent of photons, each with energy hf. So in our macroscopic world, you could kind of picture this, I think. You can't see it happening, but picture a piece of metal, light's coming in from the sun. If the individual photons that make up the light have enough energy, they could hit the electron and free the electron. And then maybe it's got so much energy that the electron actually has a little bit left over, turns into kinetic energy. So the energy that the photon has to be bigger than or equal to the work function. That's what we're saying here. So hf, this is the energy that the photon has. Photon energy. The author of the book calls it energy of electron, but really, where did the electron get the energy from? Well, it got it from the photon. So the energy that the photon donates, if you want to say it like that, to the electron has to be greater than or equal to the work function of the metal. So E sub 0 is the work function. If you want to get the cutoff frequency, take the work function divided by Planck's constant. Okay, good. And if there's anything left over, then it turns into kinetic energy. So if the frequency of the photon is less than this cutoff frequency, none of the electrons will be freed. You can't shine low energy light on a metal surface and have any electrons be freed. You've got to meet the minimum energy. The minimum energy is again called the work function. Okay, good. More intense light delivers a larger number of photons, but still, even if you have a really intense light, if the energy of each photon isn't enough, nothing will happen. You can't take a whole bunch of low energy light and shine it on the metal. Nothing's going to happen. You could take low intensity, high energy light and you will see something happen. Okay, good. So we've got some formulas here. This really, for the photoelectric effect, it's one of those topics like on a test or homework. It'll start the photoelectric effect, blah, 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 blah. Well, it's the photoelectric effect. We've only got a couple of equations that deal with the photoelectric effect. You just have to know how to use them. Okay, there is a distribution of kinetic energies when this process happens. Different electrons require different amounts of energy, but the maximum kinetic energy is, this is the part that I like to see, the maximum kinetic energy, HF minus the work function. And we saw this before. This is the energy that the photon has. Photon energy. Okay, minus the work function, whatever's left over becomes kinetic energy. And then we saw this before as well. This is, you hook up the battery backwards, you turn all the kinetic energy into electrical potential energy. We have this formula. So V stop, kinetic energy max divided by charge. But we also know kinetic energy max from up here is HF divided by the work function. So we could add that to this formula. So plug this in here. Hopefully there's not too much writing going on there. And you come up with this equation. Okay, so we've got a couple of equations we could work with. The homework has several photoelectric effect problems on it, so you'll get some practice using these formulas. So if each photon transfers its energy to just one electron, that electron immediately has enough energy to escape. The current should begin instantly with no delay, and that's exactly what experiments show. Okay, so here's an analogy to our everyday world. We can use an analogy of a swimming pool to visualize the photon model of light. A pebble is thrown into the pool, increasing the energy of the water, but the increase is shared amongst all the molecules, creates a small ripple. So classically, the energy of the pebble is shared by all the water molecules, nothing happens. But what if the energy of the pebble comes in and one water molecule could get all of that energy? Well, if that were the case, the water molecule could actually jump out of here. In real life, that's not what happens. All the water molecules share it. But what if they didn't? That would be the photoelectric effect in the macroscopic world. All the energy, one water molecule gets it, has now enough energy to leave the water. Okay, and that's kind of a synopsis of what I've just said here. So 1921, this is what Einstein actually won his Nobel Prize for, developing this photoelectric effect idea. Okay, let's see what we have here. What are the threshold frequency and wavelength for electron emission from sodium and from aluminum? Okay, so let's just do one of them. Sodium. Here's the work function. 2.75 eV. Okay, so we know that this, from what I've done before, is H times the cutoff frequency. So if you want to solve for the cutoff frequency, take the work function divided by H. That will give you this frequency. And then once you have that frequency, I'll leave this part to you, you can get the wavelength from this formula. Frequency times the wavelength. So speed of light divided by that frequency will give you the wavelength. Okay, so we have 2.75 eV, going back to this. This is for the next part, which I'll leave that to you. To get the frequency here, we need the work function. Okay, 2.75 rather. And now divided by Planck's constant. Now you saw we had two Planck's constants. Which ones are we going to use? Let's go back and take a look at those. Okay, I went back to slide 63. So 6.63 times 10 to the 34th joules times seconds, or 4.14 to the minus 15th eV seconds. Well, our energy is in eV, so we're going to have to use this Planck's constant in eV to have the units work out correctly. So let's do that and you'll see what I'm talking about. Okay, so to get this frequency then, I'm going to have to use 4.14 times 10 to the minus 15th eV times seconds. I'm running out of room here. And the reason I'm doing that is now this is an eV, this is an eV. The answer is in 1 over seconds, which that's what a hertz is. So take 2.75 divided by 4.14 to the minus 15th, and you get a really big frequency, something to the 14th power. It's about 7.5 to the 14th power or something like that. Okay, so actually put the number in your calculator and see what you get, but you'll get something really big. And then once you have that frequency, you can get this wavelength from this relationship. Speed of light, don't forget what that is, 3 times 10 to the 8th meters per second. So you've got that for the speed of light divided by the frequency that you get. That will give you the wavelength that's associated with the cutoff frequency. Okay. Excellent. So actually, here's what the number looks like. I said 7.5, so I was pretty close. 6.64. Put the numbers in, you get that for the frequency. Just make sure that you use the correct value of H, and then same thing, you can get the wavelength in this way. Okay, and then the photoelectric effect can be observed with sodium if the wavelength is 452 nanometers or less. So 452, that's the biggest wavelength. Anything less than that, you'll definitely have the photoelectric effect happen. Anything greater than that wavelength, so the bigger the wavelength, the smaller the energy, you get nothing happening. It doesn't matter how intense it is. So this includes blue and violet visible light, but not red, orange, yellow, or green. So this only happens for wavelengths that are small enough. Aluminum with a larger work function needs ultraviolet of 290 nanometers or less. Okay, so it's harder to, as you can see from the work functions here, it's harder to liberate electrons from aluminum because the work function is bigger. In other words, the ticket cost is more, right? 4.28 versus 2.75. Okay, good. So part 2 continues from this point. If you have any questions, just email me and I'll talk to you soon.